Michaelis mentioned enzymes before. Now we can look at allosteric enzymes, different type of enzyme. This usually has more than one polypeptide chain, and each one of those polypeptide chains is going to have its own active site. And they'll experience something called cooperativity, where you bind, the substrate binds at one active site, and then that's going to affect how these substrates bind at other active sites. So if you bind one, it might shift the the um, the overall protein, and then it makes it, maybe it exposes that active site, and so it's easier for the next couple to bind. We also have allosteric effectors, and these could be positive or negative. So they are ions or molecules that regulate the allosteric enzyme. So they're going to bind at sites that are other than the substrate site. And when they bind, that's going to alter the 3D shape of the enzyme, and that's going to change the actual binding pocket, like where the substrate's supposed to bind. A positive effector is going to increase the speed, right? That's going to be a positive effect. It's going to enhance the substrate binding and make the reaction go faster. And then a negative effector is going to reduce that binding. It's going to slow down the reaction. You can also see some feedback inhibition, and this is when you have a series of enzymes catalyzing a bunch of reactions. So you have enzyme 1 is going to catalyze the reaction between A and B, and then B and C will be catalyzed by a different reaction, and then C to D by another one, D to E by another one. And then once you make E, E can then feed back into step 1, and it can serve as a negative effector. Like suppose once E starts to build up, then you want to shut this reaction down because you don't want to get too much of this. When you have enough, if it's sitting around there, you're going to have enough. It'll serve as a negative effector, and it's going to stop this process. So it'll inhibit that process, and then the E will drop. The amount of E that you have there will drop. So which statement of allosteric enzymes is not true? So again, allosteric enzymes, what are we looking at? We have these positive effectors, negative effectors, you have feedback inhibition. What do we have here? So it's regulated by positive and negative effectors. That's true. Is it controlled by competitive inhibitors? Not really. So it's not controlled by competitive inhibitors. These are going to bind at sites other than the active site. So somewhere else, it will change the binding site, but it's not going to compete with the substrate directly. It's not going to be this one. Shape definitely is, for C, shape is going to change when the effectors bind. And yes, there are usually more than one polypeptide. So covalent modification is when you have an enzyme catalyzed making or breaking of covalent bonds within the enzyme. So we'll see this a lot with phosphorylation and dephosphorylation. So that's the making and breaking of phosphate esters. So down here we have this enzyme. This is the less active form, and this is the more active form. And you can kind of convert between these two forms of the enzyme. Suppose you want it to be active, you want it. This is glycogen phosphorylase, so this is going to break down glycogen. So when you need a lot of it in the active form, then you're going to want this kinase enzyme to undergo to catalyze the phosphorylation. So you can see over here, you now this thing has a phosphate group on it. So you went from the alcohol to the phosphate group. Um, when you no longer need it to be active, then you can remove this phosphate group and you can turn it into the less active form. So that dephosphorylation happens by the phosphatase enzyme, and that's a hydrolysis of this phosphate ester. So the kinase is going to make it, is coupled with ATP, so you're going to get some of that energy from the ATP, get that phosphate group over there, add it onto this enzyme, and then you can break it down to form the less active form. I think that's all that's saying there. Another example of covalent modification we see with the zymogens, where you have an inactive enzyme precursor. So something like some of our digestive enzymes, trypsin and chymotrypsin, these are digestive enzymes that catalyze the hydrolysis of peptide bonds in proteins. Now, they're digestive enzymes, they're made in the pancreas, but the pancreas has to produce them in their inactive form, because if they made them in their active form, it could actually damage the pancreas. It would kill the cells that are making them. So we make the inactive forms, we call it, instead of trypsin, it's called trypsinogen and chymotrypsinogen. So those ogens at the end mean that's the inactive form. Those are the zymogens. So you can activate the zymogens, activation of zymogens, hydrolysis of the peptide bonds. So here is trypsinogen, and then here's trypsin. Trypsinogen is 246 amino acid residues, whereas trypsin is just 240. So once you cut off those 6 amino acid residues. Now you've got the active form of trypsin. It undergoes some conformational changes. It exposes the active site and makes this thing active. And then the trypsin actually can start activating the chymotrypsin. So here's how we make chymotrypsin. The trypsin is going to hydrolyze some peptide bonds. First, it makes this form, this pi chymotrypsin, so it's not in the final form yet. And this guy actually catalyzes its own, it hydrolyzes its own bonds and splits itself up into three pieces and then connects them with disulfide, yeah, disulfide bridges. Like what? That's so crazy. So you have the trypsinogen, that's your inactive form. Then you make your trypsin, and all you have to do is cut off these. You have to just hydrolyze these couple residues here, get that out. Now it's active, undergoes a conformational change, and then it activates the rest of this process to get your digestive enzymes into their active form. And so that's going to happen in the small intestine. They're made in the pancreas, but then they would kill the cells that made them if they were